Hello and welcome to today's video where we're going to do some practice with logic laws. So in the last two videos we went through the basic logic laws and then we went through some advanced logic laws. We did a few examples of each scenario, but now we really want to be putting everything together. And this is when it's important that you've hopefully taken the time to memorize some, or you have that sheet right in front of you so you can kind of go off and look and really think about each step. So I hope you guys will practice this on your own and then kind of compare to what I do. So first one, show that P implies Q is equivalent, logically equivalent, to not Q implies not P. So the good thing about this one is there's not much that I can do. So there's not much where I can go wrong because both of these are just simple just conditionals, right? They're just conditionals where I'm saying P implies Q and not Q implies not P. But the thing is here, I know a lot of you guys are thinking, okay, I can do a truth table, easy proof. But we just want to prove them using logic laws because sometimes that's how you have to prove things. So let's try to prove this one using logic laws. Well, P implies Q. I know that by the conditional law, I can turn that into not P or Q. Okay, so now I have not P or Q. I'm trying to prove that it's logically equivalent to not Q implies not P. I haven't done that yet, obviously. They're not the same thing. But what if I can't really work with the left-hand side anymore, but I can work with this one by doing the conditional law again. So I'm going to do not P or Q is equivalent to, remember I take the not of the first one, so it's going to be not Q implies or not P. So that's what I'm at now. And then let me write down on the side what I did. So the first step I did the conditional law. And the second step I also did the conditional law. And now what I'm about to do is do double negation and do not P or Q because I see the double negation with the not Q. And remember the double negation says I can just write that as Q. So this one was double negation. And now I'm getting close, right? I have not P or Q implies or is equal to Q or not P. These are the same thing by the the commutative property. So not P or Q is equal to, and I can move this one around to be not P or Q, and that's by the commutative property of logic. And it's the same thing as all the commutative properties, which just says that order doesn't matter. So we've proven that those are the equivalent. So you can see that sometimes proving by logic can actually be quicker than proving by truth tables. So it's a good thing to know. And this one, the key was just knowing those conditional laws, double negation, and lastly, commutative. Okay. So now we're trying to prove that something is a tautology. Remember what it means to be a tautology. That means always true. So I'll write that here. So how can we prove that something is always true? Well, let's just go step by step. This question says P or Q implies Q or Q implies Q. This is immediately kind of confusing me. So Q implies Q. I want to work with that right away. I just want to get rid of that. It's kind of weird. Okay. So implies, and instead of Q implies Q, I'm going to use my conditional law and say, okay, well, I can write that as not Q or Q, right? Because you take the negation of the first one or the second one. So not Q or Q. Now, what I did there was conditional law. So now let's take a look at this. What can I simplify this guy to? Not Q or Q. Well, that's just going to be true all the time, right? I have to be one or the other. So that's a tautology. So not Q or Q is a tautology because there's no situation where one of those won't be true. Q has to be true or false. So I'm left with P or Q implies a tautology. Now I can try to do the conditional law again because I have a conditional right here, right? So again, it's the negation of the first part. And the first part in this case is going to be P or Q. And now it's going to be or the tautology. And now, so that was again the conditional law here. And here was, yeah, that was a law too. The inverse law, I think, is what that one's called. Okay, but that one's pretty intuitive, so we don't really need to memorize the name. Just know that if you have not Q or Q, that's going to be true all the time. So now this last one. Not Q, not P or Q or T. We're actually done with the proof because of the domination law. It doesn't matter what this is. If it's or a tautology, this is always going to be true because this could be false all the time. This one could be false, but if this one's true, the whole truth value is true. So by the domination law, this is true. So I can say that that just equals true by domination law. If I have or a tautology, I'm always going to be true. And logically, you can kind of think about that and it'll make sense. So we proved that's tautology, so we're good to go there. All right, so this is our last one, and this is probably the toughest one we have. So definitely try to do this one on your own, see how far you can get, and then try to watch and see what I do differently or if you got it right. So first thing, this means that we're not kind of trying to getting it to as simple as possible. We're just trying to show that this can equal this. So we just want to simplify the left-hand side until we're left with P and Q. That's our goal. So what do we need to do? Well, we need to do a lot, right? Because we're starting with a bunch of stuff. And the right-hand side, this part, the right-hand side of the left-hand side, is what really kind of gets my attention because I have P and Q. Well, I'm going to use the associative property to kind of simplify that side. That side's just a little bit lengthier and it's bugging me a little bit. So what I'm going to do is I'm going to say, well, I can rewrite this as P and P, right? Nothing wrong with that, and Q. And that was because of the associative property. So what I did is I moved around the parentheses. Instead of saying P and Q, now I have P and Q. And now let's think, okay, well, what does P and P equal? So not P and Q, and P, well, that's just equivalent to P, right? Because P and P, there's no difference there. It's just logically equivalent to the proposition P. So now it looks a little bit better. That actually looks a lot better to me. So what can I do now? I'm still pretty far from where I want to be, and I'm left with an and an or. But I can actually use the distributive property. I know that you're probably thinking, well, this is equivalent to this. They're both ands, so how can you use distributive? Because they have to be different to be distributive. Well, what if I looked at it this way? What if I looked at this one and this one? So what if I rewrote it? I'm going to write it as P and Q and not P or Q. Now all of a sudden it's clear, probably a lot clearer to everyone, that I can use distributive because now this symbol is different from this one because that's an and that's an or, and that's the type of situation that you can use distributive property. If you remember from our definition video, you can only use distributive if they are different. So now I can use the distributive property, and remember how that works. I do this one to this one with using the and symbol in the middle, and then I do that again here using the and symbol, but then in the middle of the whole thing we use the symbol that's inside the right hand side. So let me just show you what that means here. So we have P and Q, and because we're using this symbol here, and not P. That's that part. And then in the middle we put the symbol from the right hand side, which is the or. Then now we distribute the P and Q to the other side, so P and Q and Q. So this is what I have now. How can I simplify this guy? Well, there's a few things I can do. I'm going to start with the right hand side because I noticed again I have P and Q, and this is going to be the same situation as I had in the beginning. I can turn it into P and Q, right? Exact same thing I did using the associative property, which simplifies to P and Q. So that's what I'm left with on the right hand side. But now what can I do on the left hand side? Well, I have P and Q and not P. So again, all symbols are the same. They're all ands inside of this, which means I can use the associative property, and I'm going to move the parentheses around, and I'm going to use the commutative property to move the not P closer to the P, and I can rewrite this as P and not P and Q, right? All I did was move the not P next to the P and then switch around the parentheses. So I used the commutative property and the associative property. Okay, so P and not P. Well, let's think about that one for a second. If can P and not P both be true at the same time? No, they can't. That's a contradiction. So I'm left with a contradiction and Q, or P and Q. So that's what I have right now. This is what I have. But now I can simplify this one step further by the domination law. So if I have a contradiction and something else, the contradiction is never true. So the conjunction, the and of something, is never true. So I'm left with F or P and Q. And now we need to think about the identity law. If I have a proposition paired with a contradiction, that just equals the proposition. So I'm left with P and Q as my final answer. And that last step is explained because if I have the contradiction or something else, the contradiction is never true, so I'm left with just the truth value of that something else. And so that's what we wanted to prove. We wanted to show that equaled P and Q, and that's what we've done. So that's a pretty tough one there. If you can do that one, you can do all of them. Hopefully you kind of understand how these rules really help with proofs, and they give us an alternative to just using truth tables all the time. Because truth tables can take a while. Like for this one, number 3, it would have taken a very long time to do a truth table, but using those logic laws, we can simplify it pretty easily. So thanks for watching, and don't hesitate to contact me with any questions. Have a good one.